In this example, we're going to expand on that linear combination idea with I and j to talk about this trig vector representation. And this can essentially really simplify application problems. Although when we go over it, it's going to seem like it's taking way longer because we're discussing kind of a new topic and we really got to figure out how to set this up. But if I have my vectors in this notation, the calculations can be much simpler. In order for us to use this representation, we want to think about what this means. We have v, the vector, is going to be represented as the magnitude times the cosine I plus sine times the j vector. Remember, I is my horizontal component, j is my vertical component. Cosine is generally x, sine is generally y when we think about our unit circle. All right, so we're going to use that logic to kind of develop these two new vectors, which then we can very easily add together. The previous problem we worked through, we used law of cosines. The problem stated, a ship sails north 80 degrees east for 120 miles, and then south 20 degrees west for 200 miles. How far is the ship from where it started and in what direction? So we want to find x and this angle theta. We developed that triangle, which took us some time to do. Now, we're going to do this without considering this additional triangle here. So let's determine how we can represent this using our new notation. We have our first leg of our journey from A to B, and then we have a second leg of our journey from B to C. So let's think about, we'll call this vector A. Vector A is from point A to point B. The magnitude of that vector, we know the length, it's 120. And when we go to state our angle, we want to state our angle in a different way. Even though we know this was an 80-degree angle, we want to think about that as being a vector oriented in standard position, or rather a vector positive rotation off the x-axis. So that angle right there is 10 degrees, which per our definition above means I have the cosine of 10 times vector I plus the sine of the angle 10 degrees times my vector j. That's the main trick, is we need to think about the orientation in standard position from the positive x-axis, a counterclockwise rotation, the way we would travel on the unit circle. Now, let's just go back and compare this to what we have up here. 120 is my magnitude, cosine 10i plus sine 10j. Let's develop a vector for the second piece. So I'll call that vector z. The magnitude of that vector is 200. Let's think about our angle measurement, because we don't want to use this 20-degree angle. So if I were to sketch my x and y axis, and I know that my positive x-axis is 0 degrees, well, we drew south 20 degrees west. That's a little bit off of this 270 to the left. Specifically, we've moved 20 degrees. So that angle rotation we would need to use would be 250. And we would have cosine of 250i plus sine of 250j. So, again, we talked about this for quite a while, but once you understand this better, then it's a little easier for us to figure out how to set these up. And again, there's a different way I could have stated this. I could have used a smaller angle and then negated it, because I know cosine is going to be negative in that quadrant. Same with sine. So I could have used a reference angle here, for example, which would be 70, and I could say negative cosine 70i minus sine 70j. But I don't want to get in too deep with the different notations that you can use. We're just kind of beginning to touch on this concept. So if we have them in this component form, well, I can just say that my sum is just going to be A plus Z. That means I'm going to be adding my components. I have 120 cosine 10I, 120 sine 10j, 200 cosine 250I, distributing 200 sine 250j. So if I add up my I components and my j components, what it would look like would be, I would get that the sum of vector A plus vector Z are the sum of my two I components, don't forget to distribute, and the sum of my two j components. So 120 cosine 10 plus 200 cosine 250, and that's how many I have, horizontal components, 120 sine 10 plus 200 sine 250 j. Now I can calculate each of these coefficients, typing them into my calculator in degree mode. And that gives me, if I round, 49.77I plus 167.10J. This is my resultant. It's just as easy as adding those two vectors. So if I want to know the magnitude and direction, that means I just need to find the length using my magnitude formula, summing the squares of each component. And then I'll use the fact that I know tangent theta equals y over x. So let's look at how we would do that. Here I have my resultant, the magnitude of A plus Z. And of course, we would use exact values in our calculator, not these rounded values that I'm writing on the screen. 49.77 squared plus 167.10 squared. If I plug that into my calculator, I'll get 174 roughly, and that will be my nautical miles. And if you go back in your notes and look at where we worked this problem previously, you'll see we found the exact same answer. Now the number may be off just a tiny bit due to some rounding error that may have occurred, but if you did it without rounding at all, you're going to get that they're both 174 nautical miles. So I found my magnitude. Now I need my direction, and the direction comes from the angle. Tangent theta equals y over x. Tangent theta equals my y component, 167.10, over my x component, 49.77. Or rather, theta equals arctan, or tangent inverse, of 167.10 over 49.77. Typing that in your calculator in degree mode, you'll get that theta is roughly negative 73. Now we have to think about how to interpret this. Remember, we're always going to get an answer between negative 90 and positive 90 when we use tangent inverse. So where does negative 73 degrees lie? Negative 73 degrees is down here in quadrant 4. So let's go back up to our picture and think about that. We've calculated an angle negative 73 degrees. We need this angle, and we want to state that the same way it was presented, so that was going to be south a certain degrees east. In this case, if I subtract 73 from 90, I get 17. So we'll say that theta, the angle or the direction in which we are traveling, is south 17 degrees east. And again, you may be saying, Miss Stein, this didn't seem like it was that much faster. Well, it can be when you understand the notation. It really can be simplified and shorten your calculations, especially when you're dealing with multiple vectors occurring simultaneously and potentially solving a system. So feel free to go back in your notes and review or relate this to where we worked the problem before. And again, when you get to Calc 3, you're going to see a lot of this vector notation all semester. So it's nice to kind of give you a little introduction to it here in our Trig class. As always, email me with any comments, questions, or concerns.